Your HDL code and your synthesis tool will decide what your control signals are based on your coding style and some rules regarding control signal usage. First of all, each flip-flop has 4 control ports: data, clock, clock enable, and there is a set reset port. The clock enable and the set reset port are designed for active high inputs. An active low input can be used but must be inverted with the LUT to operate properly. There is no local inversion for either of the clock enable or the set reset ports. You also need to know that the set reset port can be programmed as either a set or reset, not both. Unlike older architectures, there is not a separate set and reset port available on the flip-flop. So if you want both, either the set or the reset functionality will have to be generated from a LUT and thus be a synchronous set or reset. The set reset port can also be implemented as asynchronous, although this is not as flexible. An asynchronous set or reset port cannot be implemented as a LUT input, so your synthesis tool and the implementation tools don't have the ability to map this control signal to a LUT input if it's asynchronous. You should always remember that clocks and asynchronous set resets always get access to the control ports. This is because they cannot be implemented otherwise. Specifically, asynchronous sets resets cannot be implemented as a LUT input, but synchronous set resets can. Now we'll talk more about this and its benefits a little later on. The Xilinx implementation tools, commonly called the place and route tools, take the synthesized design and map the logic to the FPGA resources. In this example, this is simply a gate to LUT exchange. So while you will code an HDL with a gate functionality, it is the synthesis tool's job to build a design netlist that includes Xilinx primitives, that is, LUTs, registers, and other resources. The map program, part of the implementation process within the implementation tools, will then group the resources into slices, effectively for speed and maximum device utilization. For the sake of our discussion, it is important for you to remember that the implementation tools will try to group LUTs that have common inputs and flip-flops that have common control signals into the same slice. This will assure good performance and high device utilization. In the cases where designers infer lots of different control signals in their design, it's those cases that prevent the implementation tools from grouping them into the same slice. In this example, we see a clock enable is built with an active low control signal. This forces the synthesis tool to map this to a LUT input, as we can see from that on the right, and uses 2 LUT inputs in this case because the flip-flop cannot invert the clock enable signal. This may cause an extra LUT to be inferred depending on the logic inferred on the LUT already. Likewise, the lower example shows both synchronous set and reset signals being inferred. Since there is only one set reset port, one of the signals will have to be driven to a LUT input to get the desired behavior. In this case, the synchronous set was chosen by the synthesis tool to drive a LUT input. Now, I would also like to ask you another question that is not shown in this slide. What if an asynchronous set was used in the lower example rather than a synchronous set? Well, the answer is that since the asynchronous sets and resets get access to the control port before synchronous set and reset control signals do, the asynchronous set would be connected to the flip-flop rather than the synchronous reset as shown in the diagram. This would then force the synthesis tool to map the synchronous reset to the LUT input. Xilinx recommends designers build with as few control signals as possible because it usually affects the device packing. This, as I mentioned earlier, is because designers don't understand their device's register resources well enough. So on this slide, we are showing flip-flops with different signal needs. Since these flip-flops don't need the same combination of control signals, they cannot be placed in the same slices for maximum efficiency. But since the lower flip-flops require a synchronous set and a synchronous reset respectively, the designer's synthesis tool or the Xilinx implementation tools can remap the logic to a LUT input rather than a flip-flop control port. When this happens, it allows the implementation tools to group the flip-flops into the same slice. And this is, of course, a good thing. Now, by the way, the reduced control set property for XST synthesis controls this result. But if you don't design with a synchronous set or reset, it won't work. So the message here is try to design synchronously with a synchronous set or reset. It is also good to note that the implementation tools automatically look to group LUTs that have common inputs into the same slice. In this example, the tools took two 5-input functions that had the same inputs and then grouped them into the same slice. So again, what we're trying to show here is you should have confidence in the tools that they will try to group what needs to be grouped in a most appropriate fashion. Likewise, in this example, the implementation tools automatically group the shift register LUTs into the same slice when they share the same input signals. So again, just like the last slide, this shows you the implementation tools are thinking about what benefits you the most, higher device utilization and higher performance, effectively by trying to group the appropriate logic together. So as we mentioned earlier, a control signal is any signal that is connected directly to a flip-flop or dedicated resource in the FPGA directly. A control set is a group of control signals driving an individual flip-flop or other dedicated resource. Managing your unique control sets is helpful to improve your design speed and device utilization. That is because the implementation tools cannot group flip-flops into the same slice if they don't share control signals. Now, we'll go through an example on the next couple of slides to help elaborate this a little bit further. So, to elaborate and explain which flip-flops can be grouped, we wanted to demonstrate a couple of scenarios where the use of control signals can allow or prevent the grouping of flip-flops into the same slice. In each of these examples, and there's 3, we're looking at a group of flip-flops with associated control port usage and asking if you think they can be grouped into the same slice. So in case number 1, flip-flop 1 had a clock enable set reset, flip-flop 2 had the same set or reset signal, and flip-flop 3 had the same reset signal. Case number 2, flip-flop 1 had a clock enable set and a reset, and flip-flop 2 has a second set signal but the same reset. And in case number 3, flip-flop 1 has a clock enable set and reset, and flip-flop 2 has a set and a not reset signal. So why don't you pause for a few seconds, think about each of these cases, and tell me if you think case 1, 2, or 3, or if any of them, are actually suitable for having all those flip-flops grouped into the same slices.